Hello everybody out there in YouTube land. Good times for all here, or Zachary Zabala if you prefer. In this video we're going to be talking about the differences between Airys diffraction and atmospheric refraction. Now both of these things can affect things, well, Airys diffraction does for sure, and so does atmospheric, but Airys diffraction is only along the horizon, where atmospheric refraction can affect things all over, not just at the horizon. I want to show you what I'm talking about. First we're going to talk about our diffraction. Okay, we have a beach right here with a person standing on it right here. Okay? Then we have over here, we're going to have a car. We're going to have a tree. Alright? Then we're going to have a building. Just putting in some windows, okay. Alright, so this is our water level right here. Alright. And they're on the land right there. Now what's going to happen is, we're going to say this is 10 miles. Now what diffraction is going to do, this is just diffraction, and this is with the human eye, not with a big zooming camera, because it changes things up dramatically, and there's so many different types of cameras, and there's one average human eye. So I went with the average human eye. Now over this 10 miles, along the horizon, now this is your horizon, where your eye level is. Okay? Because the horizon is created by your eye and by Airys diffraction. Alright? Now for a certain angle, at 10 miles, the minimum is going to be 17 feet up from there. Well, if you're only 5 feet off the ground, 17 feet is going to be more like that. You know, it's going to be actually it's going to be way down here somewhere. So we're just going to say, okay, that's 17 feet right there. Alright, so everything in here, you are not going to see across that waterway. You're going to see a building popping up out of the top from the diffraction line. Alright, that's how diffraction works. It is a band along the horizon. I've made videos about this. Go watch those. Now this is only at a perfect nitrogen and oxygen based atmosphere. You start putting particulates of dust and water all throughout it, and the angle of resolution limit will get bigger. So the further you get, it's going to be like a curve. It's going to get bigger and bigger and bigger the further out you get, and block more and more and more of that building. Now that is at just 10 miles. The minimum would be 17.5 feet above your horizon line, your eye level, and 17.5 feet below as well. That's how diffraction works. And yes, at 10 feet, it is 35. It's amazing how much diffraction actually takes. That's why they always thought the bottom of boats were disappearing and this and that way back in the day. Because at only 3 miles, it's 9 feet. Alright? So, now we're going to look at refraction. We're going to put in our diffraction line right here, okay? Because this, right here, diffraction, is a fundamental limitation of physics. It cannot be avoided, folks. Alright? There is no getting around it. There is no diffraction in this picture because of this. This is the limitation of a lens. Alright, it's Rayleigh's criterion is the mathematical equation used to find it for any lens with a certain size aperture, yada yada yada, blah 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 blah. I've gone into this. The videos are out there on my channel that explains all this stuff. So we're going to draw a city skyline, and we're going to have a building here. So remember, 17, you're 5 feet off the ground. We're going to say that guy was, so 17.5 plus 5. 22.5 feet is going to be blocked. So you might see the tops of some trees here. Okay. Then you got a building there, a building there. These are the old brownstones. But you're not going to see is the bottom 22.5 feet for sure, minimum. So we're cutting all that off. Alright, so you don't see the people walking by, you don't see the cars, you don't see the bases of the trees. And we're going to have some big buildings back here. Okay? Real big tall skyscrapers doing some stuff like that. And these are the newer ones that have all the lines in them, and you know, they're fancy. They got the little towers on top. Okay, so we got some of those. We got our trees. We can't see the city streets. Never going to. Diffraction makes that. Now, we all know we're on a flat surface. Okay, we're not going to be talking about how refraction makes things visible over the edge of some curve. That's not what this video is going to be about. It's going to be about what refraction actually does. Okay, real things that happen with refraction. Now, we know refraction is a change in the medium, right? So we have a change in the medium somewhere. Now, where this change takes place determines how refraction is going to affect what we see. So think of this as this side of the line is one medium. We have a temperature is a certain way, the humidity, all that stuff, the pressure is different. And you know they'll say a warm front's coming in or a cold front's coming in, the pressure front. Now this side is different. So we have two mediums here creating this line, this lens. Now as you'll see, the closer you get to the middle, the more you're going to be missing. See that you can barely see those trees? Let me get a different, I know I have a different, yeah, without those edges on it. Okay, medium's real close to you. Not much, refraction doesn't affect it much. Now the medium gets closer and closer to the, in between you and the object, and it does what we call lensing. Alright, things get real big. I mean huge. And then you have your buildings again. So, I don't really like that one either. Maybe this is kind of like what Rob Skiba saw in his video, where he saw the top of this here tower only and it looked real big. There you go. You know, he was seeing it like that. Right there. So it was very close to the middle, the change that he was seeing. So your diffraction is always going to be there. Now this, it's like, there's your picture, and then this is what can change. There is no seeing under a ball or over a ball or anything like that. That's just nonsense, folks. And then the closer it gets to the buildings, the more they all get back to normal. Their original size. So as you can see, refraction can change the size of everything. And it happens a lot too. Your weird mirages, let's see if I can't get a Fata Morgana in here. There you go. See this tops? Oh. See the buildings coming together right there? Now if I had a 4-foot Fresnel lens, you know, something a lot bigger, I could do this a lot, make it look a lot neater. But we work with what we have, right? But yeah, you can make the Fata Morganas, you can... Now that is if the cold front or the warm front is coming at you at a bow like this. Imagine a big thing coming in and blowing it away. Or even if it bends back the other way, you can get it to happen. See that? So that is refraction. When you have your mirages, your Fata Morganas, that's all refraction. And that comes and goes, okay? You get big magnification, get things looking normal again. So that's your refraction, and it changes all the time. Now, diffraction can change also, but there's a minimum to the diffraction. And with the human eye, it's quite big. It just, like I said, 10 miles, it's 35 feet. So we need to start throwing that word into it when we say, oh, the bottoms of things are getting cut off. Diffraction is always taking place along the horizon, folks. It's what creates the horizon. It's what separates the top of your eye from the bottom of your eye and creates a band in between. At 21 feet, it's 2 millimeters. It's still there. It's always there at your horizon. Okay? So refraction takes the picture we already have with diffraction already in play, and you can see that, let me make sure, yeah, you can see the bottom diffraction line there. So sometimes we see just diffraction, super clear pictures. The ones Joshua Nowicki was getting, super clear atmosphere and all that kind of stuff. There might have been some refraction taking place in there, but that was mostly probably just diffraction, cutting off that straight band along the bottom. Now refraction, like we saw in Rob Skiba's video, and many other videos, where you see the tops of buildings being cut off just like that. You know, they're perfectly in view, and you can take pictures of them and everything, and they look great. Now, one way we can check to see if refraction is taking place is to know the actual size of the building, the actual distance, and know how tall it should actually be, the angular size of it. Then we can see if that changes. Okay? So I just wanted to throw that out there. We need to start using that word too, diffraction. When we start actually talking to real people about this, like scientists and stuff, getting into real arguments, getting our points across with the masses, we need to start throwing that word into there. Because they leave it out all the time. Because it totally destroys their globe model and the way it works. Because they didn't calculate that into their curvature calculator. That is their curvature calculator, diffraction. And refraction is just, it changes it a little bit, you know. Actually, it can change it a lot, as you can see. But let's start using that word a little bit more, folks, diffraction. Alright? So there's a difference. Diffraction is always taking place, and refraction most likely is always taking place, but it can be very, very small and minute as to how it affects things if you have a really nice, dry, clear day. Okay? So you have your diffraction, which is that line across the bottom that will be straight along the whole horizon. As you see, it'll create that weird looking blue band of water and the band of air, or whatever you want to call it. That is your diffraction line, not a refraction line. That is diffraction. Then you have your refraction, which takes that picture that you've already made with that lens and can do all kinds of sorts of crazy things to it. Okay, so I just wanted to clear a little bit of that up. I hope some people start taking heed of this and using the word diffraction, because if you notice, the Globers avoid it at all costs for a reason. They don't want to talk about it. Alright? They tell me that I'm making it up. It's hilarious. So please, people, start using this, because they have no answer for it. Okay? So that's it. Good Times for All here, signing out. As always, thanks for watching.